Hi everybody. There have been a few questions about one of the videos on the College Board's YouTube site, and the video talks about I and J, and I decided to make a short video to explain what these mean and make sure we can clear up any questions you have. So the question says, a ball is thrown with speed v naught at an angle theta above the horizontal. Find the net change in the velocity from t equals 0 to t. So you can see here that she used these notations of I and J. So let's go through what that actually represents. So I'm going to start with what you already know. You know about vectors. And in your pre-calc class, you learned about polar coordinates and rectangular coordinates. So a vector starts at the origin and has an angle as measured on the coordinate plane from 0 degrees, and has, or we could do it in radians, and it has a length, which we'll call r. And you learned how to convert a vector from polar coordinates to rectangular coordinates by taking x equals r cosine theta and y equals r sine theta. And again, we've got polar coordinates, r theta, and rectangular coordinates, x, y. Okay. So that's what you already know. And when we went to solve problems in this class, I told you to never cross or never mix the horizontal and vertical information. The only thing that can go between the horizontal and vertical information is time. Otherwise, if we were working with velocity, for example, we would use the horizontal component of velocity, and if something were launched at an angle, that would be v naught cosine theta, and vertical velocity would be v naught sine theta. Okay. So now let's look a little bit closer at this new notation. So basically, here's what I and J represent. Instead of calling these axes x and y, we're going to call the horizontal one I and the vertical one J. And these are not just labels, they're directions. So I means the horizontal direction. And because it is this direction indicator, I'm actually going to make this little caret on top, which indicates that it's a vector direction. It's a direction. I'll do the same thing for J. I think she actually does sort of a cursive J, and that represents the vertical direction. And these are actually called unit vectors. So that if I had a vector of length 1 in the I direction, this would be 1I. And if I had a vector of length 1 in the J direction, this would be 1J. Now we know that that's not how we add vectors. We don't add vectors tail to tail. So let me move this over. I could represent this resultant vector R. I could say that vector R is equal to 1I plus 1J. In our class, we talked a lot about how do you add vectors, and you add them head to tail. So here's the head of the first vector and the tail of the second vector. And the resultant goes from the tail of the first vector to the head of the last vector. And we're saying that this blue path here is equivalent to following the purple and red path. And this would be, this R equals 1I plus 1J would be another way to write that vector R. Now, Now let's see what happens if we're not just using the unit vectors. The unit vectors again have length 1. Let's consider an example with which we are somewhat familiar. Suppose that's 3 and that's 4. This vector R, I would say, is 3 units in the I direction and 4 units in the J direction. So vector R would equal 3I plus 4J. And in fact, we know that the length of vector R would be 5 because the way that these add is using the Pythagorean theorem, not just by adding in a linear fashion. This is not a linear picture. Let's say I have another vector. Let's say to this, I were to add another vector. Let's just say that's a 1 by 1 vector. Oops. So in the horizontal direction, it's 1I. Oops. I'm getting my fonts mixed up here. And in the vertical direction, or in the J direction, it'd be 1J. And if I were to add these two vectors together, I'll rename this first one R1. So if I were going to add R1 plus R2, what would I do? I would add the horizontal components, and I would add the vertical components. And that's what we did in class. We added components of vectors together. But this unit vector notation is just another way to indicate that. So 3I plus 1I would be 4I, and 4I plus 1I would be J. 4J plus 1J is 5J. And that would be the vector sum. And indeed, if I look at this, I know that this is not really to scale, is it? But this would be 4 in the horizontal, and this would be 5 in the vertical to get to that resultant point. Okay, so let's go back to her graph and take a look at it. I'm going to zoom in here. She's got a nice picture of the initial velocity of the object. And let's just clarify it a bit. The horizontal component would be V naught cosine theta. That's how long that component is. Now let's do the vertical component. The length of the vertical component would be V naught sine theta. Again, those are just lengths. They're numbers. Just like down here, this length is 4. Okay. We're going to use those numbers, or she uses those numbers in her solution. So she says that the initial velocity of the ball is V naught cosine theta. Okay, that was my horizontal. And then she puts this unit vector on to indicate that this just tells everybody that this is horizontal. Then she does the same thing in the vertical direction. She said, the vertical amount, the magnitude is V naught sine theta. And then the J indicates the direction, and the direction is vertical. All right. Then she did the same thing in the final, for the final velocity. And to get the final velocity, she took the initial velocity. What the heck did she do? And then she used a formula to compute, she used a kinematic formula to compute the final velocity. So she's got the horizontal component again here. Now this horizontal component didn't change, right? Horizontal component of an object moving in a parabolic path doesn't change. So these two values are the same. And when she subtracts them, when she subtracts these two things, they zero out. Then in the vertical direction, again, she used a kinematic to get the final velocity. Here's the kinematic that she used. Part of it cancels out. This V naught sine theta part cancels out, and she's just left with negative GTJ. So the change in velocity is a vertical one, and it's equal to the acceleration of gravity times time. Okay, hopefully that makes a little more sense when you realize that really what she's doing is just lining up the horizontal and vertical information, and the horizontal information is on the left, the vertical information is on the right, and she's keeping it separate just like we did in class. What if you were doing this problem? How might you approach it? Well, here's what I would say. In the horizontal direction, delta V is 0 because there's no acceleration in the horizontal direction. In the vertical direction, I would say that the definition of acceleration is delta V over delta T, or delta V in the vertical direction is equal to A delta T, and in the vertical direction, the acceleration is negative 9.81 meters per second, which, by the way, does correspond to what she says here, because I'd have to go back and double check. My brain is mush, but G was 9.81, and then she adds the negative on there. And then the delta T, they say that the change in time is from 0 to T, so we're just going to call that T. And then the units for that are meters per second. So the delta V sub Y would be a different way to indicate the same thing that she did. You know, by separating it like this into horizontal and vertical, you get the same answer with just a little bit different notation. They are both correct. Okay, I hope that helps. Please let me know again if you have questions, and I will do my best to answer them with a helpful video. I'll talk to you soon.